So welcome you to today's module. So what we were discussing in the last module was basically introduction to statistical hypothesis testing problem, which is described as follows. So you have a given statement or a given hypothesis which is to be tested against an alternative statement or alternative hypothesis. So the hypothesis which is to be tested, we call such a hypothesis to be null hypothesis, and the hypothesis against which null hypothesis is to be tested is called alternative hypothesis. Then we give a definition of a test function, which is in general a randomized test function. We realize that any randomized test function can be represented as a function from sample space to 0, 1. So such a function could be phi x. So phi x denotes the probability of taking x and a 0, which is probability of accepting h naught, and 1 minus phi x would be probability of taking the other xn, which is probability of accepting h1. So then we saw that when you use any test, there are two kinds of errors which might happen. Or your loss function is L theta a, where a is a0 and a1. So there are two kinds of loss which may occur. That means although h naught is true, you claim that test claims that h naught is not true. So that is one kind of error. The other kind of error is although h naught is false, but your test says that h naught is not false. So in terms of, so everything, because when we talk about a risk function, we talk about expected value of the risk loss function. So in this case, expected value of these errors would be probability of type 1 error and probability of type 2 error if your loss function is 0, 1. That we saw in formulation of testing problem as a decision problem. So the best thing would be if I can find a test for which both probabilities of both of these errors is minimum. We saw that that is not possible because of presence of some undesirable test which always reject h naught. For example, one test could be which always reject h naught, which controls one type of probability to the minimum possible, but for this test the other kind of probability is the maximum. So minimizing both the kind of errors simultaneously is not possible. So we said that what you do is you try to fix a bound in one kind of error which you consider to be more serious. So first you identify the error which is more serious. So we said that I'll frame my h naught and h1 in such a way that type 1 error is more serious. That means probability of wrongly rejecting h naught is serious. So I put a bound on that as alpha, which we call as a level of significance. And then among all tests having a level of significance alpha, we try to find out a test for which probability of type 2 error is minimum, which is equivalent to saying that probability of power of the test is maximum. Power is nothing but 1 minus probability of type 2 error. So the first result which we did in that direction was the Neiman Pearson lemma, which tells you that if you are testing a simple hypothesis against a simple alternative, a simple hypothesis is hypothesis which describes the probability distribution completely. So that means f is same as f0. So you know that it says that your distribution function is f0, which is totally specified to you. There is nothing unknown in the f0. Against a simple alternative hypothesis, and Neiman-Pearson lemma gives you the most powerful test in such situations. Then we did one result that if you have a one parameter family, and this family is such that it has a MLR in theta and Tx, then also for testing h naught theta less than or equal to theta naught against h1 theta greater than theta naught, or h naught theta greater than or equal to theta naught against h1 theta less than theta naught, you can find the uniformly most powerful test. And we saw that such a test has very nice properties. Now there are other kind of tests which may be possible. So one test could be h is less than or equal to theta naught, h is less than or equal to theta 1, or h is greater than or equal to theta 2, that means theta lies in the tail, or h is in the interval, h is between theta 1 to theta 2. Now for these kind of tests also, uniformly most powerful test of level alpha may be possible if you have exponential family. So let me do that result, which is about the exponential family. So your P is f theta. Theta belongs to capital theta. where theta is a subset of R, and your f theta x, that means joint PDF of x1, x2, xn is same as c theta e to power q theta tx into hx x belongs to Rn, theta belongs to theta. Q theta is strictly increasing, or decreasing, as the case may be. First understand what does q theta is strictly meaning. That means if I consider f theta 2x upon f theta x, it will be q theta 2, c theta 2 upon c theta 1, which does not depend on x. Then e to power q theta 2 minus q theta 1 into tx. So if q is increasing, then q theta 2 minus q theta 1 will be positive, so this would be increasing in tx. So it would have a MLR if q theta is strictly increasing. Whereas if q theta is strictly decreasing, then it will be decreasing in tx. Decreasing in tx means larger values of t would correspond to small values of theta. And when it is q theta is strictly increasing, it has MLR in theta and tx. That means larger values of theta correspond to larger values of tx. So let us consider first situation. So let theta 1 and theta 2 are two given points, be fixed constants, such that theta 1 is less than theta 2. Consider testing h naught, that theta less than or equal to theta 1 or theta greater than or equal to theta 2 against so let theta 1 and theta 2 be the fixed points in the parameter space capital theta, and suppose you are interested in testing h naught that theta is less than or equal to theta 1 or theta is greater than or equal to theta 2 against alternative hypothesis theta lying between theta 1 and theta 2. So the situation is like this: theta 1 and theta 2 are fixed constant given to you in the parametric space. Your null hypothesis is that theta is either here or here, and you're testing such a hypothesis against the hypothesis that theta is between theta 1 to theta 2. In such a situation, there exists a UMP alpha test. So there exists UMP alpha test given by, of course, you can tell by intuition what would be the test. Note that when q theta is strictly increasing, the larger values of theta corresponds to larger values of t. Here h naught is saying h naught is saying that theta is in the extreme. So that means if q theta is increasing, this fact would get reflected in the data through t taking extreme values. So that means tx is less than or equal to c1 or less than or equal to c2. And this would get captured by t lying in an interval c1 to c2. So you would reject h naught with probability 1 if tx is between c1 and c2, because your h naught is that tx would take values in the extreme. Gamma ix, if tx equal to cn, I is equal to 1 to 2. And 0 otherwise. And how these c1 and c2 are chosen? Where c1 and c2 are positive constant, such that what you do is e theta 1 phi x So that means that is the boundary point. E theta 1 phi x is same as E theta 2 is same as alpha. Note that this is the test for the situation when q theta is increasing. Q theta is decreasing, then larger values of theta would correspond to smaller values of t, or smaller values of t would correspond to larger values of theta. So in that case, the test would get just interchanged. So it would be tx less than or equal to c1 or tx greater than or equal to c2. So in that case, it would be tx greater than or equal to c2, and rest of the thing as it is. Now, another thing is among all tests phi's which satisfy this test phi naught minimizes the probability of type 1 error also. Not only that, it minimizes the probability of type 2 error. Among all tests which satisfy this, it also minimizes the type 2 error. So that's a very nice property of this test. And this is similar to the property which was possessed by the UMP alpha test when we were dealing with one parameter family with MLR. So that is what the second part says. For every theta belonging to theta with theta less than theta 1 or theta greater than theta 2. That means your theta is falling in the null hypothesis. The test in A minimizes the power function which is the reward beta phi theta, which is expected value of phi x, among all tests satisfying star. So this is a result. So this turns out to be very useful, especially in situations where you are dealing with hypotheses of this kind. So what we have seen is in one parameter families, uniformly most powerful tests exist in all these situations. So our natural question arises is, if I had a nuisance parameters, whether in this case, so in place of just theta, I had a theta and phi. So if I had a nuisance parameter, whether even in these situations, UMP alpha test exists, or even in the one parameter case, whether UMP alpha test exists for other kind of hypothesis. So one such hypothesis could be theta is equal to theta naught against theta not equal to theta naught, where theta naught is a fixed constant. Now one can see that in general, UMP alpha test for such a hypothesis does not exist. So let me write down this as a note. In general, UMP alpha test for testing H naught that theta is equal to theta naught against H1 that theta not equal to theta naught, or for testing H naught that theta is in an interval against H1 that theta is less than theta 1 or theta greater than theta 2. So in neither of these cases, even in one parameter families, in general the UMP alpha test does not exist. Although in some situations it may exist. For example, one may see whenever you are dealing with a truncated family of distributions like uniform 0 theta, in such a situation UMP alpha test may exist even for this situation. Normal case it may not exist, right? And in fact one can easily see that in situation wherever theta is equal to theta naught against theta greater than theta naught, if you are testing that, or if you are testing theta less than or equal to theta naught against theta greater than theta naught. If the UMP alpha test which you obtain is unique, then in those situations, UMP alpha test for these situations will not exist. One can prove that, because what would happen is if, for example, in normal case, if UMP alpha test exists for theta less than or equal to theta naught against theta greater than theta naught, then UMP alpha test would also exist for theta greater than or equal to theta naught against theta less than theta naught. So if you want level to be alpha, certainly optimal tests should utilize the maximum liberty given to it. So you would like to have a power function to be alpha at theta naught, right? Because the requirement is the power function should be less than or equal to alpha at. So your error should be, probability of type 1 error should be less than or equal to alpha. So the best test would certainly like to utilize the maximum liberty given it to you, so that it can then do some trade-off with probability of type 2 error. So such a test, for such a test, beta phi theta naught would be alpha. If beta phi theta naught is alpha, one kind of a test would be one-sided test for theta less than or equal to theta naught against theta less than theta naught, theta greater than theta naught. So it would reject for large values of x bar. For other hypotheses, it would reject for the small values of hypothesis. So you will get two different tests. And one can prove that the UMP alpha test does not exist. So how to deal with these situations, or even with situations like this, but you have a nuisance parameter. Now, in such cases, UMP alpha test normally doesn't exist. Now, the UMP alpha, if UMP alpha does not exist, what I try to do? The natural thing I try to do is I try to restrict my class of test procedures under consideration by imposing certain reasonable condition on the test functions to be considered. And then in the restricted class, I try to find out the most powerful test. And one such reasonable restriction is that of unbiasedness. So that means I require my test to be unbiased, which simply says that the level of significance should always be less than or equal to, because level of significance is the upper bound on type 1 error, should always be less than or equal to power. So power should always be, because you would like power to be larger, and normally alpha would be smaller. So you would expect that power to be at least as large as alpha. Any such test is called an unbiased test. So power is greater than or equal to alpha. That means probability of type 2 error should always be less than or equal to 1 minus alpha. So if alpha was fixed at 0.01, probability of type 2 error should be less than or equal to 0.99. That is what I would expect. And that restriction is required so that you can get rid of tests like phi x equal to 1 almost everywhere, or phi x equal to 0 almost everywhere. So unbiased test and uniformly most powerful. So I have roughly defined what is unbiasedness. So such a restriction is required so that you can eliminate test procedures which reject h naught all the time. That means phi x equal to 1 or phi x equal to 0 all the time. So a test phi is said to be unbiased at level alpha if expected value of phi x is always less than or equal to alpha for every f belonging to P0. So your hypothesis is the same, right? H0 that f belongs to P0 against H1 that f belongs to P1. So this ensures that your test phi is of level alpha, and what do you expect? probability of rejecting H naught when H1 is true is always greater than or equal to 1 of alpha, is greater than or equal to alpha for every f belonging to P1. So this is the probability of rejecting H naught, because x equal to phi x is probability of rejecting H naught when H1 is true. So this is a power. So power should be greater than or equal to alpha. So that means power should be greater than or equal to level of significance. Now this is equivalent to saying that expected value of 1 minus phi x would be less than or equal to 1 minus alpha for every f belonging to P1. What is expected value of 1 minus phi x? Probability of accepting H naught or not rejecting H naught. So it is probability of not rejecting H naught should be less than or equal to alpha for every f belonging to P1. So that means probability of not rejecting H naught. So you are not rejecting H naught although H1 is true, which is same as probability of type 2 error. So it says probability of type 2 error should be less than or equal to 1 minus alpha. So unbiased test is one for which power is always greater than or equal to level of significance, or equivalently the probability of type 2 error is always less than or equal to 1 minus alpha. So power, this is equivalent to saying that power is always greater than or equal to level of significance. So what I do is let alpha is a fixed level of significance. So what I do is I consider all those unbiased tests which have a level alpha. So let us define du alpha as collection of all those phi's which are a map from Rn to 0, 1 such that expected value of phi x is less than or equal to alpha for every f belonging to P0. That means all those tests which have a level alpha, and for them power which is expected value of phi x when f belongs to P1 is always greater than or equal to alpha. So this is the class of all unbiased tests of level alpha. So what we'll do is I'll try to find out a best test in this. A best test means the one for which probability of type 2 error is minimum or the power is maximum. So I say that a test phi naught is said to be uniformly most powerful unbiased test of level alpha so which you also call as UMPU alpha test. If for any test which is unbiased of level alpha, that means phi belongs to du alpha, the power of phi naught, so that means EF of phi naught x is always greater than or equal to the power of any test in any unbiased test of level alpha. And power E of f phi x becomes a power when f belongs to P1. So for every f belonging to P1. So that is our goal. So we'll see that in many situations one can find such a test. So next module will derive a result which gives you UMPU alpha test in situations where you cannot find a UMP alpha test. First of all, note that a UMP alpha test is always a UMPU alpha test. So let me write down a small note. Phi naught is UMP alpha implies that phi naught is UMP U alpha. Why the thing is very simple, because I consider this to be the class of all level alpha test, provided it exists, because you see, provided phi naught exists. If it exists, then it would be UMP alpha, because phi naught may not exist, UMP alpha test may not exist. So this is a class of all tests under consideration. What does UMP alpha test does? UMP alpha test finds the best test over here, that means for which power is maximum. And these are UMP alpha test. So a UMP alpha test, provided it exists, would be a UMP alpha test, provided any UMP alpha test is also unbiased. Can you say that any UMP alpha test is unbiased? Yes. Why? Because consider the test phi no data x as alpha for every x. Does this have a label alpha? It certainly has a label alpha, because expected value of phi x is always alpha. So expected value phi x would be alpha for every f belonging to P0, and a requirement for label alpha is expected value phi of x would be less than or equal to alpha for every f belonging to P0. So this has a label alpha. If this has a label alpha, then I know that UMP alpha test has a power more than this. So expected value of phi naught x would always be greater than or equal to expected value of phi n dx. Why? For every f belonging to P1, because phi naught is the uniformly most powerful. So its power would be greater than or equal to power of any other label alpha test, and phi nd is a label alpha test. So UMP alpha test always belongs to UMP alpha test. And this phi naught was best among all classes of estimators of tests, so it would be the best among this restricted class also. So this suggests that if UMP alpha test exists, then it would be UMP alpha. So finding UMP alpha test makes sense only when UMP alpha test does not exist. As we have seen, in certain situations UMP alpha test may not exist, especially when you have a nuisance parameters, or you have a two-sided hypothesis of the kind theta is equal to theta naught against theta naught equal to theta naught. So in the next module, we'll present one result which tells you how to find UMP alpha test in situations where UMP alpha test does not exist. So that we'll do in the next class. Thank you.